Hello everyone and welcome to today's Technology Talk webinar session. For those of you who don't already know me, my name is Marie Karekla and I am AIRAH's Engagement and Program Coordinator. So today's Technology Talk presentation is presented by Big As Fans and it is on sustainable HVAC design using air movement in the air conditioning buildings. But just before we go into the presentation, if you do have any questions for the presenter today, please type them into the Q&A function that's located just at the bottom of your screen, and we'll do our very best to get through as many questions as possible within the time permitting. So now I'd like to introduce to you our presenter for today, who is Ario, who's the sales engineer at Big As Fans. So Ario, I will pass things over to you and you can get our presentation underway.
I would like to start this presentation. It's pretty dense, so I'll go straight into what are we going to talk about. Yeah, so today we're going to talk about thermal comfort, right? Also with ASHRAE 55. How can we control thermal comfort as an engineer? How do we pair HVAC with fans? Some application examples, and a bit of bonus, the ancillary benefits of elevated airspeed. Yeah, each of these on its own is pretty dense. So I'll continue on. A bit about me. So I graduated from two universities. One is UQ as a mechatronic engineer, and the other one from QUT as an electrical engineer, another bachelor. So I did 2 bachelor degrees. You have my contact details there. Previously, before I worked with Big As Fans, I work in the R&D for environmental sensors, servicing the mining sector. Right, so I came into Big As Fans because I want to further my interest on sustainability and energy efficiency in especially cooling and heating of buildings, because we know global warming is already here, and building contributes about between 40 and 50% of that emission. A bit about who we are, why the name Big As Fans. So actually, we started producing HVLS fans, the big diameter fans, to cool cows. In collaboration with the farmers there in the US. So when we put the fans there, the cows actually produce more milk, and then obviously the farmers are very happy, and they kept referring us as Big As Fans because it's Big As Fans, and that's how the name got stuck, right? We are the world's largest manufacturer of HVLS fans, right? We have about 700 employees with 60 engineers, right? We have 6 global offices. I myself is in Australia, and we have actually a facility, R&D facility, LEED Gold certified, where we test fans, right? For design and for performance reasons. And we also are a member of major ASHRAE committees. Now, getting to thermal comfort. Yeah. So what is thermal comfort? So thermal comfort, based on the ASHRAE 55, is a condition of mind which expresses satisfaction with a thermal environment and is assessed by a subjective evaluation. To keep it short, it's like, are you comfortable with where you are in terms of thermal environment? Pretty much it. I highlighted subjective evaluation, as we're going to talk about that in a couple of slides further. So having comfort means, lack of noticing discomfort, right? And it sort of helps with focusing on the work or activity at hand. Yeah, you can imagine if you, say, work in an office where temperature is about 30 degrees, you'll be quite distracted. Yeah, and as I said, with subjective evaluation, each person perceives particular thermal comfort quite differently. Now, why is thermal comfort important? Thermal conditions are potentially life-threatening. As you can see in the table here, right? Our core body temperature lasts between 36 and 37 degrees, and that's a normal range, right? Above there, hypothermia are fatal, so heat stress, and below there is hypothermia. Again, it's also fatal. And the way we regulate our body temperature is called thermoregulation, right? And it actually depends on heat gain and loss in the body. So I have this equation here for you. So the rate of heat gain or loss equals to metabolic heat gain or loss, radiant heat, convection, evaporation, due to sweat and work. I'm going to get into more details here. So for us humans, as you can see in the diagram, we gain and lose heat through different avenues, right? We have solar radiation, and then we lose heat through evaporation, respiratory. We got breezes that coming in, that's convection that help us to lose heat. We also radiate our heat to the environment, right? Because our core is 37, say our ambient temperature is 34, we radiate to the air. Conduction as we touching the ground, etc., etc. So, apologies. So, food that we eat acts as an input, right, for us to work and to sustain our metabolism. To maintain our metabolism, we generate heat, right, because we need to keep our body temperature 36, 37 degrees. Some note here that if you do an activity, muscle contraction have about 20% efficiency, meaning the energy that you put into contracting the muscle, 80% of it is lost as heat. So that's how we generate heat when we do an activity. Yeah. And then our body signals perception of either I feel hot or I feel cold due to this heat gain or loss, right? Or in other words, deviation from normal range. We have a process called homeostasis in our body that keeps our body at the same setting, if you want to call it that way. So any deviation from that homeostasis range creates discomfort. Your body actually does not like to change. So at best, in terms of thermal comfort, it might affect work at hand. So if you've been to a freezing office, say 18 degrees, right? You're shivering and then you can't focus and whatnot, so you might complain. And at worst, say if you do road works in 40-degree heat, yeah, that's heat stress and can be debilitating. Yeah. So why is it subjective evaluation, right? Because we as humans, we badly perceive absolute temperatures. So our skin doesn't actually measure absolute temperature, 24 degrees, 27 degrees. It measures it in categorical, I feel hot or I feel cold, right? It's a combination of physio, which is sensory, our skin, and psychological phenomena, interpretation of that sensory input. And also previous exposure or say acclimatization influences perception. As you can see here, there's a person who's swimming in the frozen lake and he feels very comfortable. I wouldn't be. And and another, this beautiful couple here in the middle of the desert, also smiling. Again, I'll be sweating, right? So acclimatization. So this creates two impacts. As I said before, people doesn't feel absolute temperature. They feel hot, warm, cold, freezing, etc. So it's categorical instead of numerical. Impact two, because of the acclimatization, people have their own comfortable temperature range. Say in an office, maybe 4 out of 40 people might complain on a 24-degree C, 50% humidity, air-conditioned office. You cannot satisfy everyone. Luckily, ASHRAE 55 took note of this. So they created two metrics, PPD, which is predicted percentage of dissatisfied, meaning because we cannot satisfy everyone, if we can achieve at least 90% of people satisfied, we're good. And then we have PMV, which is predicted mean vote, meaning, okay, we feel temperature as a categorical value, no problem. We shall put a number on it. So we have -3 being cold, right? 2 + 3 being hot. And then a good, the number that meets the ASHRAE 55 standard is actually between -0.5 to +0.5. So you feel neutral, right? You feel comfortable. Now we jump into the factors that affect thermal comfort. Yeah. So there are 6 factors that ASHRAE 55 has identified, 2 personal and 4 environmental. So personal is clothing insulation, the clothes that we wear, our metabolic rate, meaning the activity level that we do. And then environmental is airspeed, velocity, or do we have any breeze or not? The air temperature, right? The percent relative humidity, and also radiant temperature. Okay. Now I'm going to talk about personal factors first, which is clothing insulation. Now, as it says on the name, insulation meaning, yeah, it acts as a thermal resistance. And pressure 55, decide the unit to be clo. Now, clo is not a SI unit, so it has an equivalent in meters squared Kelvin per watt. So 1 clo equals 0.155 meters squared Kelvin per watt, right? And each different clothing setup have different value. For example, here, buck naked is 0, and then shirts and shorts with shoes, 0.53, semi-business suit, 0.73, and full business, 1.39. So there are research that have been done on this. Also, there are research that have been done on ethnical clothing. So if you design a facility for a particular ethnic group, you can grab their clo values from there too. And the way it works is each particular clothing item has its own clo value, and then at the end you just add them up. You wear shoes, socks, underwear, trousers, polos, you add them up, it's 0.41. Okay. Of course, it's an insulation, so that unit looks familiar because it is a unit for thermal resistance or R values. Probably you've seen this in buildings, yeah? And here's a formula for that, which is the R value equals the thickness divided by the thermal conductivity of its material. So I'm using an example of R5 insulation material here that we use in Australia. So R5 have about 5 meter square Kelvin per watt thermal resistance, generally about 240 millimeter thickness. In comparison, 1 clo equals 7.4 millimeter thickness of that insulation. Just to give a what do you call it? Imagination of what it looks like. The second personal factor is metabolic rate. Yeah, so it measures body heat production per unit area, and it's dependent upon the activity level that you do. So again, Met is not an SI unit, so it is the SI equivalent. So 1 Met equals 50 watts per square meter. So if you're sleeping, your Met is about 0.8. If you work in the office, it's 1.2. If you do picking and packing, 1.7. Do bricklaying, 3. And then shoveling, 6.5. And if you do a full athlete run, it's 9, right? So considering this example, so a heat generated by 1 Met is about 104.4 watts. Yeah, assuming the surface area of our body is about 1.8 meters squared. And then we move on to environmental, which is air temperature. Yeah, so there are 2 measures of air temperature: dry bulb and wet bulb. Dry bulb is actually the temperature of physical gases in the air, or what we call ambient. It's called the true thermodynamic temperature. Whereas wet bulb is slightly different. It's lowest air temperature that can be achieved through evaporative cooling to 100% humidity. So wet bulb actually defines the limit of ambient temperature without mechanical service. Yeah. Now, if our core, TC means core temperature, is less than ambient temperature, well, certainly heat gain is possible, right? Ambient temperature is dumping heat into our body, so it's good for warming the body. And then if core temperature is greater than TA, heat loss is possible, which is it's good to cool the body. And this is the diagram of the thermodynamic processes, right? It flows from high temperature to low temperature. Yeah, and this actually generates work. If you want to reverse it, of course, we have to input work into it. Now, a bit of a conundrum here, that, okay, if that is true, that TC is greater than TA heat flow is possible, and our core temperature is 37 degrees, then why do we feel warm or hot at ambient temperature of 30 degrees, right? I mean, we're still losing heat to the environment. The answer to this is because of the heat rate gain or loss, right? Our body senses that, okay, we cannot dump heat fast enough. Therefore, our body signaling to us that, hey, you feel hot. I need to ramp up my evaporative cooling in terms of sweat. That's why we feel hot. Okay, another environmental factor is humidity. Yeah, again, they have 2 measures: absolute humidity, so total mass of water vapor concentration in the air. But the thing that we want to focus on is the relative humidity. this is what we normally use in thermal comfort. Yeah. Again, the definition is ratio of current water vapor mass divided by the max water vapor mass in the air can hold at a particular given temperature. Because air can hold different amounts of humidity at different temperatures. There's a diagram for that. Now, a good thing to note here, an important thing to note here, that at equilibrium, 100% humidity, relative humidity air, evaporative cooling stops. Simply because you cannot dump more water vapor into the air due to the evaporation of sweat. Yeah, so evaporation sweat to cool off, no longer possible. This also explains that, say, in a high humidity state, for example, such as Queensland, the swamp coolers are not as effective, right? Because humidity is already high in the first place. Now, there's a combination of air temperature and relative humidity called the heat index. So this is what we perceive, temperature that we perceive when we combine a particular temperature with a particular relative humidity. As we can see here, say if we add temperatures to 27 degrees, humidity at 40%, we feel as if we're 27 degrees, right? As the humidity increases, say to 90%, we actually feel 30 degrees. So plus 3 degrees, right? And it's true for other temperatures as well. So actually the higher humidity, because it limits our evaporative cooling, we feel hotter. Yeah, and there are zones here that you must take caution. So the heat index between 26 and 32 degrees, it says that fatigue is possible. Continuing it would result in heat cramps. As you go in higher and higher, you'll have heat cramps, exhaustions, and heat stroke. Now, if you work outdoor, exposure to full sunshine can add up easily up to 8 degrees C of heat index because we have increased radiant heat, right? So the radiant heat here goes up dramatically. Talking about radiant heat, we're talking about the sun, yeah? So before we talk about the sun, we talk about radiant heat transfer. So it is heat transfer through photon or electromagnetic waves. And it's a reminder for us all that all material objects radiates heat. It's approximated by black body radiation. So our body, 37 degrees, air temperature, 24 degrees, we radiate heat. That we are losing heat due to radiation. Now, with the sun, yeah, it gives life, but it also, prolonged exposure causes cancer because it generates a lot of heat energy. On its own, it generates about 6.42 times 10 to the 7 watts per meter squared. When it reaches the Earth, about 150 million kilometers, it's about 1,000 watts per meter squared. Now, in Australia, it can easily be above 1,100 watts per square meter. But let's use this number for now. Say if we expose to direct sun, just to give a number on how sun's radiation is actually a huge thermal load. Yeah. So let's assume that, we're at the beach and half of body surface area is in direct contact with sun's ray. The radiation that we get from the sun is about 900 watts. Yeah, using that 1,000 watts per square meter. So that's about a microwave's worth of radiation, of heat energy, heat power, sorry. Now to compare, at 9 met rate, when you do a full run, it's about 939.6 watts. Yeah, so it's as if you're generating heat while you do a full run, just by standing in the sun. Yeah, it is a huge load. And hence why we develop building envelopes to, not let that sun radiations go through as much so that we feel comfortable. Yeah. So this is the indirect way. We have building envelopes, right? So some of that solar radiation is absorbed by the envelope, conducted throughout those envelopes. We might put insulation there, and the building envelope provides thermal resistance and hence reducing the sun's heat load being transferred into the occupants inside. Another environmental, which is air velocity. Yeah, air velocity, impact rates of evaporation, and convection cooling. Yeah, I forgot to put an arrow here. So it's higher convection cooling and high evaporative rates. and its cooling rate is proportional to airspeed based on this equation, right? So convection equals to H times surface area times the difference in temperature, right? That H, our convection coefficient, has V infinity, which is your airspeed, yeah? And you'll find this in many heat transfer textbooks. So I'm using one of them here. So let's assume that we have arm skin. So our arm, sorry, yeah, assume skin, both arms, about 20% of total skin surface as an isothermic plate. Again, just to give a number on convection cooling with 1 meters per second airspeed blowing over it. We have the parameters here, and then the convection cooling that we feel is about 404 watts. So that is not bad. So that's about, if we compare to the sun's radiation, it's about half that, right? So convection cooling can be one of the ways to increase cooling rates, although not the only one. Now, I have to press on the point that all 6 factors work together and are equally important, right? None of these are more important than the other. So make sure in your design phase, you take account of all. Okay, so that's the numbers and physics behind it, right? So how do we determine thermocomfort based on ASHRAE 55, right? Luckily, they have come up with a couple of methods here. We got graphical, analytical, elevated airspeed, and adaptive method. Some of you might be familiar with the graphical method, which is a cyclomatic chart. Now, in the recent 2020 update, they took it up. So graphical method, no more, right? So we have access to all other 3, but not graphical. Why was it taken out? Because it is limited in usability. It has a quite restricted range of thermocomfort inputs. So as you see here, requirement for use is mechanically conditioned space. So if you want to design a space without HVAC, you can't use this. Occupant activity level from 1 to 1.3 meg. So again, it's an office space. Yeah, if you want to design for like gyms, for example, you can't use this. Clothing worn, 0.5 to 1 clo. Again, about office space as well. Less than 0.012 humidity ratio and airspeed less than 40 FPM. 40 FPM in our parlance, SI is 0.2 meters per second. So at 0.2 meters per second, we actually feel no airflow. Only above that our skin can detect an airflow. Say if you want to design a space with elevated airspeed, yeah, we want to put fans in, you can't use this. And then from AIRAH block themselves, the graphical method is incorrectly more lenient with significant errors possible in certain conditions. Hence why they take it out. So what can we use then? Well, we can use this one, analytical method, yeah, or CBE thermocomfort tool. So the University of California, Berkeley created this, yeah, and put it on the web for all of us to use. And I thank heavens for that. Here's the link. If you want to go there, if you don't already know. So given a combination of thermocomfort factors, right? Operative temperature, airspeed, relative humidity, metabolic rate, cooling level, and then you can create your own custom solar gains, local discomfort, etc. It spits out PMV, PPD, and also the diagram here. Yeah, and it will tell you, oh, does it comply with the standard? Given this input, yeah, it complies with the standard. Yeah, and with this diagram here, so red is where you are, whereas the blue zone is where the range where it meets ASHRAE 55 thermocomfort standards. So use this instead. Now, I want to do a quick talk on 2019 NCC updates, which is National Construction Code. So in 2019, NCC was updated because they wanted to meet 26 to 28% reduction target in national emissions. So the background for this in 2015, the government created a doco that acknowledges effect of global warming and how should we approach it. And this is one of the initiatives that comes out of that. Yeah. So volume 1 update focus on reducing energy consumption by a potential 35% for commercial buildings. They added new verification methods to demonstrate performance requirements with neighbors and Green Star and other equivalent. It's in NCC. In the residential space, new heating and cooling load limits for NATHERS compliance. Yeah, so NATHERS is another one that calculates performance requirements for residential space. So, neighbors and Green Star. Probably you've heard of it. Probably you haven't. So in NCC Volume 1, Section J specifies that neighbors and Green Star are part of the verification methods to demonstrate compliance with what? Energy efficiency performance requirements. So now they're looking at energy efficiency in buildings. If you go to Section JV1 in that NCC, right? The use of neighbors is only for Class 5 buildings, and the particular neighbor type use neighbors energy or energy for offices space building, you need to reach 5.5 star minimum. Also, additional thermal comfort targets apply. For Green Star, it can go from Class 3 to 9 buildings, plus common areas of Class 2. Green Star design plus as-built ratings need to comply with simulation requirements and be registered. Yeah, so they have it all in the NCC. Again, additional thermal comfort targets also apply. What does that thermal comfort targets look like? It's here, right? So a thermal comfort level between PMV of -1 to +1, right? So it's a bit more lenient than the ASHRAE 55, which is 0.5 to +0.5. It is achieved across not less than 95% of the floor area. So they also include coverage. It needs to cover 95% of floor area. Of all occupied zones, not less than 98% of the annual hours of operation. So they're looking at the time as well. So 98% of hours of operation. So both neighbor and Green Star ratings measures energy density of building. So in a megawatt hour per square meter, and assigns a rating to it. Like for example, before neighbors of 5.5 star, etc. Right? And buildings needs to meet a minimum specified neighbors or Green Star rating for compliance on top of the thermal comfort targets that we talked about. So it seems like with this new NCC, the goal is, okay, how can we maintain thermal comfort levels with reasonable energy performance, right? So answering that is key to meet both energy performance and thermal comfort compliance. Well, in Queensland, I don't think we're gonna see HVAC demands coming down soon because it's only getting hotter and hotter by the day. In fact, there's a prediction that by 2050, we're gonna see triple the demand of HVAC. Yeah, so we're gonna live with HVAC regardless, well, whether we like it or not. So how can we do that, but also not damaging the environment through the greenhouse effect and et cetera, et cetera. That's what the government's trying to push. Okay, so we talked about thermal comfort and the NCC update that includes thermal comfort in it. As an engineer, how can we control thermal comfort? What inputs or variables do we have? Yeah, if we go back to the thermal comfort factors, right? Unfortunately, we do not have control over personal factors, so clothing insulation and metabolic rate. Yeah, we cannot direct our clients to wear certain clothing, right? Probably except for OHS and company policy, and also metabolic rate. We can't order them to jump up and down and then stay put in your seat, right? So again, we have no direct control over personal factors of thermal comfort. But what we do have control is the environmental factors. So what I love about engineering is we are terraforming the environment. We have control over the environment. Yeah. So we have control over airspeed. So through the plenums or overhead directional fans, we have control over air temperature and humidity through mechanical services, and we have control over radiant temperature. Not so much the sun, but at least the amount that's getting into the building through building envelopes. So insulation, glazing, etc. Okay, talking about building envelopes first, we will be familiar with this. Wall, ceilings, windows, doors, foundations, la-di-da-di-da. Yeah, it shields the occupants from solar radiation and the environmental, the harsh environmental outdoors, wind, wet weather, dust, etc. Insulation raise thermal resistances, hence lowering heat flux through the walls. So that's through radiation, convection, or even conduction. Yeah, a bit of a diagram here. So double glazed windows. Do you know that some companies actually sell R7 insulation called Bradford? I didn't know that until I did my research. Also on the roof, thermoreflective paint, yeah, to reflect more of that sun's radiation. And within that building, we have all methods of heat transfer: radiation, convection, conduction. And then number 2 is mechanical service or HVAC. Good thing about mechanical service or HVAC is directly control air temperature and also humidity, plus inject a bit of low air speed into the room, right? So it directly interjects the thermodynamic process. That's what I like about HVAC. Because when we control the ambient temperature, right? So we reduce the ambient temperature per se, we increases the overall cooling or heating potential. Yeah, cooling potential. If we increase the ambient, then we increase the heating potential. Yeah, because thermodynamics flows from hot to cold. That's why HVAC is so good. And also it lowers the humidity levels. So we talked about heat index before, so it does lower the heat index. And with lower humidity levels, it increases our evaporative cooling potential through sweat. Yeah, a bit of the heat index here. Say previously, unconditioned space, 30 degrees C with 65% humidity, we feel 34. Now we chuck HVAC in. Now we feel 27 degrees and 50% humidity. So heat stress risk reduced. Good for us. And lastly, we talk about fans, right? So fans, unlike HVAC, does not directly control air temperature, but it does control airspeed. Yeah, that's what fans are built for. It injects elevated airspeed with wide coverage into the room. Depending on the fan design, this could be between 4 to 7 times its diameter. That it'll cover that much area. Now, because fans have to abide by the laws of physics, it has to suck air from somewhere and distribute it somewhere else. It also acts as air moving equipment, right? And add air mixing air blender, because it is like a blender. It mixes the air up. So with an elevated airspeed, we increase the convection cooling potential and also sweat evaporation rates. For fans, we can perceive up to 6 degrees of cooling effect, and also destratification. So because we're mixing the air up, so we can have homogeneity of air temperature from floor to roof. For heating applications, this is important because hot air is at the top and you actually want that hot air to be at the bottom where the occupants are. Yeah, and I've highlighted the convection coefficient with the airspeed here. Now, to further talk about fans, because fan has such a wide coverage, it's also an air moving equipment. It also provides homogeneity of air temperature across wide spaces. So not just destratification, but also across wide spaces. So that's what horizontally. Yeah. So if you have hot and cold spots in the facility, fans can help with that. Again, as I said, it's an air moving equipment. So for duct design, this might be important because we can sort of offload transport of conditioned air from branch ducts. Yeah, they're coming out from the main ducts to the fans. So hence, you can reduce number of branch ducts and diffusers. We're going to talk more on this down the slides. I want to talk about the cost of control. Yeah, each control has a cost. So building envelope, certainly it's not cheap to build. It's gargantuan, and it might not also cheap to run. Yeah, in terms of its energy density, we spend a lot of energy in constructing it, but it could be very low after that. Yeah. Some notes here. Again, as I said, it shields occupants from sun's radiant heat, environmental hazards, and it's needed regardless. We do need building envelopes. Mechanical service, initial cost to buy is not as big as building envelopes, but it's still huge. Yeah. In some applications, it might not be practical to do so. Say in the warehouse, as a 100 meter by 50 meter warehouse, it's huge to install. But also a huge cost to run as well, because we're interjecting the thermodynamic processes, right? It is great for direct air temperature and humidity control. It's also energy density high when it's running. Now, I mentioned here that when we pair this with low cost control, we can save about 9% of electricity per 1 degree set point. I'm going to talk about that down the slides. And lastly, we talk about fans. Compared to the other two, fans low cost, right? Running maintenance and cost is also very low. Just to give a bit of a number here, efficient fans runs about less than 50 watts for residential, and at the bigger diameter fans, say 7.3 diameter, it runs less than 1.5 kilowatt at max speed. So the energy density is pretty low. Yeah, it doesn't control air temperature, only airspeed. But pairing it with HVAC, right? If we can offload some of that cooling load from HVAC to the fans due to increased convection cooling, we can get the best of both worlds, right? We can save a bit of electricity. Then we have control over temperature, humidity, airspeed, coverage, and ductwork production, etc. Yeah, this fits various buildings easily without blowing initial and running costs, and it helps with destratification. So, what do we do, right? As I said before, building envelope is needed. Can't do much about that. HVAC, in most circumstances, is needed to meet thermal comfort standards. In some areas, we can't let go of HVAC. However, its usage will affect the energy density of the building. So how do we reduce energy density while maintaining thermal comfort? So some suggestions here. We can have better insulation, right, in the building envelope side. So double glazed windows, R5+ insulation. You go with thermal mass design, passive cooling, etc. Oh, so not passive cooling, sorry. We can have more efficient HVAC system. So there's this thing called DOAS, paired with air economizers. Equipment upgrade, replace the old HVAC with the new one that is more efficient. HVAC maintenance and cleaning. And lastly, we can also pair HVAC with fans, because we are floating the cooling load from HVAC to the fans, right? We can sort of increase its thermostat by 3 degrees, and we can save electricity through that. So 9% of electricity per 1 degree of increase. 3 degrees means 27%. And there's a couple of independent studies that acknowledges this. Depending where you are, average is 9%, but it could be between 6% to 9%. Which that's what I'm going to talk about here. If we decided to go with the third route, how can we do that? How can we pair HVAC and fans? Yeah, and I'm going to use thermal comfort tool for this. So let's say we have a scenario. 1, HVAC only. So it's a standard office building. These are the thermal comfort inputs. So 23.8 degrees air temperature, 23.8 degrees radiant temperature, relative humidity 60%. Airspeed is 0.15 meters per second. Yeah, metabolic rate is 1.1 met, and clothing insulation is 0.6 kilo. When we chuck this thing into CBA thermal comfort tool, what do we get? It says, yep, we complies with ASHRAE standard 55. All is good. Yeah, conditions based. Now, what if we add fans to it? As I said before, if we add fans, due to increased convection cooling, we can increase the HVAC thermostat set point. So now let's increase that set point by from 23 degrees to 26.1 degrees. And because we have elevated airspeed due to fans moving, airspeed has increased from 0.15 to 0.6 meters per second. Same building, same parameters, except the air temperature and airspeed. Yeah. What do we get? So this is what we get. It also still complies with ASHRAE 55. This is 2.3 degree set point increase. But same PMV, same PPD with the previous example. The benefit gain is we save electricity, about 20% electricity save. That is not bad. How far can we push this? We said I said initially that fans can provide up to 6 degrees perceived cooling. So let's push this to the max, right? So I increase the set point by 5.6 degrees. It still also complies with ASHRAE 55. Yeah, and with a bigger electricity savings, about 45% here. So that's how fans can help with energy efficiency and energy savings. Now, some application examples here. To support those, I will also talk about ductwork minimization. Am I good? Okay. So we have school in Lexington, right? 727 square meter. They initially wanted to go with HVAC. So this is the diagram. We have the main trunk here, and then we have the branch ducts, right? Set point of 20 degrees. Of course, there's no fan, so it feels like 20 degrees. Materials and installation for this, when they were in the design stage, when they're approximating it, is about 57,000 or 58,000, and about $80 per square meter. Yeah, and then when they compare it with fans, right? Because we have increased convection cooling, right? We can increase the set point by 3 degrees, but it still feels like 22 degrees. And when they did the approximation of the cost, it's about 53,000, so lower than previous, and about $73 per square meter. And I have the comparison here when they're actually measuring the energy usage. The cooling heating only for this consumption, by using fans, we achieve about 38% reduction only for that facility, and total electricity consumption about 17% reduction, just by incorporating those fans, right? We're incorporating 1, 2, 3, 4 fans there. This is the design render with HVAC, and also design render with fans. Yeah, as you can see, there's not much ductwork at the top, so you can save costs on that. And with fans, it's sort of open up the roof space as well as an additional thing. a tool in your belt for you to use. Also, we have an office space. Again, they want to go with HVAC only, so we can see the main and the branch ducts. Set point 23, feels like 23. Material installation is about, say, 34,000 or $60 per square meter. And then they want fans in, right? In comparison to fans. Again, not many branch ducts, because fans will move, will suck the air and move it throughout the room. We can increase the set point to 25 degrees, and it still feels like 23 degrees. The material installation drops by about what? That's about more than half. So that is not bad. Yeah, and this is the comparison. Yeah, there's about $19,000 difference between the cost, AC and in comparison with AC and fans, and then 24% reduction in consumption for cooling heating only, and 11% reduction in total electricity consumption. Yeah, and this is design render for that office space with HVAC, and this is with fans. Now, some more close to home example, Australia, Darwin International Airport. So we actually put about 10 of our Essence fans there. They receive about 2 million passengers a year, and they have a cooling problem, big cooling problem, because they have foyers, they have large doors, they have to frequently open them. So you've used a lot of energy to condition the air within that facility, but now it's being let out, right? So it's a constant battle keeping the terminal at consistent, comfortable temperature. So they need to consistently lower HVAC set point than designed for guest comfort, because they receive complaints. So what they did at outcomes. So the senior engineer, Glenn Newport, decided to install 10 of our Essence fans, 2 meter diameter. Because of that, again, increased convection cooling, they can increase the set point by 2 degrees, right? Without any passenger complaining. So it's good on them. And then that 2 degree set point is actually enough to trigger, they have an air economizer system as well, 410 hours of air economizer operations per year. And because of that, they saved 203 megawatt hour electricity, or about 57,000 cost savings per year. So they're very happy with the solution. Yeah. Another one that is for heating, right? This is British Airways at Gatwick Airport at the UK. They have huge problem. It's a plane hangar with very, very tall ceiling. Problem in heating issue. So they have heating ducts at the top, right? That dumps hot air down, but because hot air rises, it never actually reach the occupants, right? Or very few of those hot air reach the occupants. They have an extreme 10 degrees temperature gradient between floor and mezzanine. despite they spend a lot of money on that sophisticated heating system. So the heating system has to work at full blast 24/7 because the temperature set point sensor is at the occupant level and the set point can't be reached. So they just work full blast. So the electricity bill was astronomical. Yeah. So they approach us and then we send our engineers there to look at the facility. This was before my time. And they install about 7.3 meter power fans. So the biggest diameter that we have. Now, because they've installed the fans act as the air moving equipment, so it actually pushes the hot air down to floor level. The heating system actually turned off automatically for the first time. They didn't know that they have that capability because set point was reached, right? So they were, based on the stories that I've heard, they called our engineers saying, "Oh, your fan tripped our heating system. Come in and fix it." So our engineers went there and checked the heating system and actually told the engineer at Gatwick Airport, actually, your heating system have automatic shut off. So because set point has been reached, it shuts off automatically. When the temperature is not at that set point, don't worry, it will turn itself on. Yeah, and because of this, they saved 2 gigawatt hour of electricity. That is huge. And this is within 3 months, right? About $114,000 saved during first 4 months of operation, right? So they ROI, they reached the ROI within 3 months. Fans paid off. Yeah, and this is the data that they gave us. So before, when the fan is off, this is in Fahrenheit. But as you can see, there's a massive temperature difference between 1.5 meter, so floor level, and about 10.5 meter. When the fan is on, that provides destratification. Yeah, it's sort of level. Although you can see the spikes because they have to open the hangar doors and whatnot, but the temperature now level. So that's the benefit of destratification. Okay. Am I good with time? I think so. So I want to talk about the ancillary benefits of elevated airspeed. Right? So we talked about, okay, it can save electricity when paired with HVAC. It provides destratification. It can save ductwork cost because you can offload that moving the conditioned air to the fans. I'm going to talk about again, destratification, right? So destratification, it is a classic case, right? As I said before, heated air rises and hover around the ceiling level, and most of the time, thermostat at occupant level, and that's a problem. So if we put fans in, it'll push the air down and circulate it, and hence maintaining consistent flow-through temperature. Yeah. And then another ancillary benefit is actually productivity. I talked about comfort, thermal comfort, and how it can distract you from work before. There are a couple of research that has been done on this. I have the reference right here, right? So for every degree above 25 degrees C, right, you would induce a productivity loss, right? Because people are distracted, they don't feel comfortable, or they might be sweating, especially at the elevated temperatures, right? So because fans can provide up to 6 degrees of cooling. Yep, 6 degrees of cooling. So say if we are at 29.4 degrees, yeah, and then we put fans in, then we can bring the productivity loss down back to 0. Yeah. In a warehouse example where they can't put HVAC in, it is imperative because they can have less frequent heat breaks due to sufficient cooling rates that's provided by fans, convection cooling. So I think we're at the end of our talk here. I'll give you a summary. So what have we talked about? We've talked about thermal comfort definitions and factors. We've talked about the S-Tray 55, the PMV, PPD, the methods, which was the CB thermal comfort tool. We've talked about the NCC update with neighbors, Greenstein thermal comfort compliance. We've talked about controlling thermal comfort. How do we control that? Building envelope, HVAC, and fans. We talked about application examples, the gym, office, the International Airport and British Airways, and we've talked about ancillary benefits, certification and improvements in productivity. Yeah. Last thing before we close and go to Q&A. Now, we built this CFD simulation from scratch to reflect the ASHRAE 55 standard. So it does include PPD and PMV. We call this thing Spec Lab, right? So as you can see here, it does give you a airflow map that shows if you put fans in the facility, what's the coverage going to look like and what's the airspeed going to look like, right? And how would it affect PMV, PPD, et cetera. So this is one example of that result. This was automotive repair facility that they want to put 2 fans in. So they can't afford HVAC, so they approach us. Okay, Ario, I want you to put fans for me. So I did, and before the fans, of course, there's no cooling effect and there's no cooling coverage. But after the fans, if you put the fans in, it has 1.28 meters per second airspeed, so that's pretty high. Perceived cooling effect of 5.72 degrees, and with that 2 fans, it covers 98% of their facility floor area. And as you can see here with the PMV, without the fans, their PMV was 1.87. With the fans in, it's 0.7. Yeah, this one, it certainly does not meet the ASHRAE 55 standard because it needs to be, less than 0.5. But for unconditioned spaces, at least we can, with fans, it can improve the thermal conditions, and that's the goal. Thank you. That is all.
So the first question we do have there, Ario, if you've got it up on your screen, is someone's asking what ceiling height for an office building will be recommended to install fans without going too high on air velocity.
Okay. Office building. Okay. So for office building, because you don't want, as you said, you don't want the air velocity to be greater than 0.8 meters per second, because that's where the paper starts to flutter, right? So you want to keep it below that. For ceiling heights, obviously the taller the better, but we have 1.3 meter diameter fan, 1.5 meter diameter fan that can fit a standard ceiling height of 2.4 meter. If you want the bigger fans, say the 2.1 meter and above, the clearance guidelines looks a bit like this. So if we have, say we go with 3 meter diameter fan, right? It needs to have clearance from the floor to the fan blade of about at least 1 fan diameter, so 3 meters, right? And depending on the fans that we select, right? If it's an essence fans that we have, 600 millimeter clearance from the fan blade to the ceiling is enough. If we go with the more industrial fans, like our powerful range, then you need clearances between 1.2 meter to 2.1 meter, depending on its diameter. Certainly, the 7.3 meter requires 2.1 meter clearance from ceiling to the blades. Does that answer the question?
Yeah, no, thanks, Ario. The next question we've got here is from Jonathan, who's asking, in office, what airspeed would be safe to avoid vapors from flying around? And are there any drawbacks for using, obviously, your fans?
Okay. So I'll answer one at a time. So as I said before, Jonathan, we would like to keep the airspeed less than 0.8 meters per second, right? So 0.6, 0.7 is ideal. And the second one, is there any drawbacks using bath fans? Was that the one?
Yeah, that's correct.
Any drawbacks using the fans?
Yeah.
That is an interesting question. Any drawbacks using the fans in an office building? Yeah. Personally, if it's paired with HVAC, I don't see there is a drawback in using the fans unless the client does not want to have fans. I've had clients through a third party that come to me. So the engineer wants to move the clients away from HVAC. So we run the simulation for the engineer, and then the engineer talked to the client and said, client insisted no HVAC, no fans. Yeah. You might also with fans, with lighting, there might be a drawback with lighting. Say if you have lighting directly above the fan, because fan has blades and the blades move, it might create a strobing effect. For some occupants, that might not be ideal. Yeah. So lighting. Hope
Thanks,
that answers
Ario.
the question. Yeah.
Yeah.
Okay.
Look, we've got a question here from Grace, who's kind of asking a couple of questions here. But the first one is, with the fan on graph for British Airways, is that operative temperature or dry bulb temperature? And second one is, how much does it matter that there is stratification if cooling is delivered to the occupant on the lower level? Therefore, comfortable? Is it only linked to location of return air grills?
Okay. Okay. Could you keep this question, Marie, so that I can see it? Okay, I'll answer one at a time. With fan on graph for British Airways, is that operative temperature or dry bulb temperature? That's the temperature within that building. So it'll be the operative temperature. How much does it matter that there's certification if cooling is delivered to the occupants on the lower level, therefore comfortable? Is it only linked to location of return air grills? Well, if cooling is delivered to the occupants at lower levels, well, that's good, right? You might not need fans, but say if you want to have some energy savings out of that, right? When you can increase the set point from say 24 degrees to 27 degrees, then fan is a way to do so. Yeah, it's just a tool. It's just fans are is a tool in your belt to achieve a bit of energy savings that increase HVAC set point temperature, and also if you have hot and cold spots on the office space, then you can use fans too, because it will deliver that airflow. It will deliver that conditioned air there. Hope that's good.
Thanks, Ario. Yeah, all good.
Yep.
Next one here on the list there is from Mark Ario, who's saying, with recent research into virus transmission from the pandemic, how does the increased air velocity affect virus transmission and spread?
Okay. To be honest, I'm not sure about this question. I do not know. I'm not a medical professional here. Yeah, I'm so sorry, Mark.
Well, good. Thanks, Ario.
Yeah.
Another one here is, are there any noise implications with the fans?
Yes. Noise implications depend on what fans you get. Now, a good fan good fans should not generate any noise from its motor, right? Say if you have a residential fan or an office fan, right? Say our fan Hvac, the noise it generates only from the movement of air, right? And same with the industrial fans. So I think for the residential fan, the max noise level is about 35 decibels. So that's pretty quiet. If you're talking about directional fans, right? So it's not HVLS, but high speed fans, then you would have some noise. Yeah, and that noise could reach 70 to 80 decibels.
Thank you.
Yeah.
Another one here from Dario is, any case studies of combined HVAC plus fans in a supermarket environment?
Supermarket environment. For the projects that I've done, I have nothing to give you, but I can liaise with my colleague in either Canada or the US or the Singapore, or even to my boss Dan, that see whether we have it. If you do need it, yeah.
Thank you. And Jonathan's asking, can you use UV lights with your fans?
Oh, yes. For our Hvac range, yes, we have a UV light on them if you want to put them in.
Perfect. I think that's all the questions today, Ario. I know there's a couple of ones around COVID-19 spread, and obviously, like you said, you're not in a position to best explain that. Yeah. So we might wrap it up there, everyone. We do have Amber has put in the chat box a bit of a link there if anyone wants to. There's a special offer at the moment. If you would like a customised, no obligation spec lab, please follow the link that Amber has put in the chat box there for you guys. So just want to wrap up today's session, and of course thank everyone who attended and registered today for the Tech Talk. And of course, a special thanks to Ario as well for conducting such a great presentation.
No problem. Hope all of you get a use out of it. And let me know if you have got any feedbacks or whatnot.
Yeah, no, certainly. And look, the recording is made available as well. So if you do want to go back and watch it again, everyone, that will come up in the next couple of weeks, and I'll send out an email to everybody as well, and let you know when that does become available. Of course, if you wish to get in contact with Big As fans, please feel free to either contact myself or get in contact with them directly for further information. If you do wish to register or view any of AIRAH's other upcoming Technology Talk or Streamline sessions, there is a full list of March and April sessions coming up on the website, so feel free to check those out. And please remember that you are eligible for 1 CPD hour as well for your attendance today. So thank you, everyone. Thank you to Ario and Big As fans. Great presentation, and I look forward to everyone joining me once again soon. In the meantime, take care, everyone.
All right, guys. Take care. Stay safe.